thank you all for coming to this early check on this lovely, rainy Amsterdam day. I'm really happy to be here, and I'm really happy to see all of y'all here as well. I'm going to start with a little introduction about myself. My name is Em. I am a consultant at ThoughtWorks. That means that I go work with different clients, and I teach them about how to do agile software development. I teach them about how to do continuous delivery. I travel working with lots of different people on lots of different cases that they're trying to solve in the software world. My graduate research is in economics, specifically experimental economics. I studied under Kevin McCabe, who wrote papers with Vernon Smith, which were some of the pivotal papers in the field of experimental economics. And Kevin McCabe, my advisor, was a neuroeconomist. And what neuroeconomics is we would give people drugs or hormones, or we'd stress them out, or we'd put candy bars in front of them after telling them not to eat for 3 hours. We'd somehow aggravate them or make them feel really good, or somehow change the chemicals in their brains and then study their decision making and try to understand exactly what is going on. Why does adrenaline result in this sort of behavior? Why does oxytocin in the brain result in this kind of behavior? So that's where I got my statistical chops, doing experimental economics with human subjects in a laboratory in Virginia in the United States. My background, so while I was doing this, I was writing Python and I was doing R and Stata or Stata, however you say it, and doing also data analysis with Python. But my background is I have a religious studies degree. And so after 3 years of PhD program, I flunked out, which is totally fine. I think flunkouts are some of the best data scientists. No bias there, I mean. And so nowadays, especially because I'm working sometimes with people who don't have data, teaching them to do continuous delivery, I'm an operations engineer, I'm a back-end developer, I'm a front-end developer, I'm a data scientist. So I feel I have a quite uniform distribution of skills across the software space and the data space. And that's where I am now. So this talk, I mentioned in the description that the field of data science is having an identity crisis, but it's kind of always had an identity crisis. There are people in the room who've been doing data science since before it was called data science. There are people in this room who are doing data science who probably wouldn't feel comfortable calling themselves a data scientist, but other people would. It's not really clear what it is to be a data scientist sometimes. Is a data engineer also a data scientist? Is a person who works with data but doesn't call themselves a data engineer also a data scientist? If I just do some machine learning but I don't productionalize it, am I a data scientist? There's a lot of different questions about the identity of what it is to be a data scientist. This often comes down to, I don't know how to identify it, I don't know how to define it, but I recognize it when I see it. Sometimes we don't recognize it when we see it. It's not clearly defined, but I think there's some commonalities among the people who are somehow calling themselves or called by other people a data scientist. So I want to talk in a way that helps people understand what it's like to be a data scientist, or what it's like to think like a data scientist. So let's talk about that. What does a data scientist do? One of the first ones, the easy ones to think about, is that a data scientist is doing predictions, categorization, clustering, somehow using models to extrapolate on the real world to make some sort of value judgment, or not value judgment, but prediction or judgment about what the future might hold or what the state of reality might be. Data scientists also are writing software. I think the common statistic that's floating around is that 80% of a data scientist's time is spent writing software that transforms or cleans or collects or somehow gets the data ready to go into a machine learning model or a linear regression model or some sort of model that does this other one, predicting, categorizing, clustering. There's a lot of software that's written just to be getting into that other point. And then finally, communicating data. So making visualizations, making Jupyter notebooks or some sort of notebooks to communicate to other developers on your team or your product owners, your stakeholders. Sometimes you need to make visualizations just to communicate to yourself in 2 weeks, because what the heck was that person thinking 2 weeks ago, and why did they do this particular model, or why did they clean the data in this way? So some of the things that are often thrown around about data scientists, what are they? They're people who do models, they write code, they communicate data. This isn't too controversial. I don't think I mentioned, I want to make this talk both descriptive and prescriptive. So the next point is a little bit of a quip and complaint about the state of data science and about what people are doing with data scientists or to data scientists in the world today. The next thing that's kind of true about many data scientists in the industry is that they're thrown into an organization to somehow make money for the company. There's somehow, we're going to just hire a bunch of data scientists, maybe we'll give them access to data, maybe we won't, maybe we'll make them fight for years to actually be able to get access to the data, but somehow they're going to fix the problems. They're going to crunch the numbers, they're going to make our lives better. So let's hire $1 million worth of data scientists and let's make some money somehow. So to recap, we have code plus models plus communication and visualization of the models plus some magical things that happen. And all that comes together to get us the business value that makes data scientists worth it. This is, in my opinion, in my interpretation, talking to lots of data scientists within ThoughtWorks around the world, and also talking to people at conferences and my friends, this seems to be the pattern for what happens to make data scientists useful. And there's a big question mark that nobody knows what we're doing in that one place. So now I introduce my controversial opinions that try to address this question mark of what are we supposed to be doing. So here are some controversial opinions about data scientists. First, they should be good software developers, and they should know what an API is. Maybe they shouldn't be experts at making APIs, but they should know how to get their model into a place where other people who also write code can access and query that model. So a good data scientist is somebody who knows how to get their data science, into a place where people can use it. I also think that a good data scientist should be competent with continuous delivery. They should be able to make pipelines, and they should be able to do it with infrastructure as code. This is because data science models have shelf lives, and being able to get the model into production so that people can query it and use it as fast as possible is the only way to guarantee that the model that we're throwing up into production and using is still valid. It takes a long time to develop a model. It takes a long time to productionalize a model. And the model might not still be good enough or fresh enough if we don't get it up there as soon as possible. And so having data scientists in an environment where they're doing continuous delivery, whether or not they're writing every single line of infrastructure code or just on a team that's also doing this, the only way to make sure that our model, or the best way to make sure that our models are working as they're supposed to be, the way that they were designed, is to get them up there as fast as possible. I also think that data scientists should be able to speak the business language and work with stakeholders and business owners about KPIs. Why am I building this model? Who's going to use it? What's going to happen once it's in there in production? Thinking about the business gives the data scientist purpose and also gives delivers the business value to the business. This is one of the steps that can help turn that question mark taxidermy monkey from the slide before into actual business value. That's the thing that can make the equation actually balance out. And I'd posit if these things aren't there, then you can have great, brilliant data scientists, but I think you're underutilizing them. So maybe I should have made this word might like a different color, because I think that lots of data scientists are very useful even when these things aren't happening. But I think, or maybe I should have said they're not used optimally. That would have been really nerdy. But the point is, you can use them. You can use your data scientists better if you're doing these things. So that's how a data scientist should work. But we're here to talk about how does a data scientist think. So let's move on to that. How does a data scientist think? The spoiler is that a data scientist thinks like an any other scientist, but we're going to answer this question with a story about cholera, because who doesn't want to hear a story about cholera at 10:40 in the morning on a rainy day? So let's talk about cholera. I kept the yay in there. So I'm going to give you some cholera facts first. Cholera is a deadly bacteria that can kill within hours. Historically, it's killed millions and millions of people. It's been very terrible. Basically, when you contract cholera, all the water in your body tries to come out in like every way possible. It's not a very pleasant experience, and it kills within hours. Luckily, it's curable, and 90% of the cases of cholera can be cured with like a really, really cheap solution of salt and sugar and water. It costs about 10 cents per dose. Oral rehydration therapy is one of these breakthroughs where it's like everybody in the world should have access to this. There's no reason for people to have cholera anymore because the solution is so cheap to make, and the technology to make it is also not, there's no barriers to entry to making the cure for cholera. It used to be a problem in London, also everywhere else in the world, and it's still a problem in the world today. But I'm going to talk in particular about the problem that existed in London in the 1800s. So the cause of cholera and how it spreads, or how it was spreading, was unknown in 1854, in the time period that we're talking about. The leading theory about how cholera spread was miasma theory. So this comes before germ theory, and this is literally the concept of bad air, that bad smells were carrying things in them that caused people to get sick. This theory had an interesting property in that when you held this theory to be true and you worked to remove the bad smells, you happened to remove the actual things that were causing people to get sick. So it had an actual good feedback cycle where it held enough water. If I remove the thing that smells bad, usually rotting flesh or human waste or something like this, if I get rid of the bad smelling things, people stop getting sick so much. So it seemed to be a pretty good theory for a pretty long time. This is why you see these plague mask doctors. So what they would do is they put a good smelling or a clean, sterile smelling thing inside of that beak, like rose petals or vinegar and a sponge or something like that, basically to cover up or replace the bad smell, the miasma, the thing that was causing the sickness. So this way, doctors felt protected because they weren't breathing in the bad smells that they thought would actually kill them. So let's talk about the particular outbreak on Broad Street in London that's called the outbreak of 1854. There was a guy named John Snow, and he did a remarkable thing. What he did was he looked at the data, and he wanted to understand. He didn't buy this miasma theory very well, and he wanted to understand, maybe it's not the odors, maybe there's something else. So he looked at the data to try to understand what's going on. One of the things that John Snow did was he looked at a map of London in general, and he looked at the distribution of where people were contracting cholera and dying. So this is going through several months or days of the cholera outbreak. I promised code, so I'm going to do a little jump to Jupyter Notebook and talk about distributions for a second. So if you don't know, this is also one of the things data scientists do, and one of the ways that, one of the tools that we use, it's called Jupyter Notebook. Not too many data scientists these days are using the language I'm using called Julia, but often people are programming in Python in this thing, and it's nice because it gives a quick feedback about, you can import data sets, you can visualize your data, you can rearrange your code. There's a little bit of a gap between doing this and doing continuous delivery and test-driven development and things like that, and we need to figure out how to solve that in the industry. But anyway, here's Jupyter Notebook. I'm just going to show some distributions. The first thing I wanted to show is this normal distribution. So there's a couple assumptions that we make in science, and these things are either often that things are going to be either normally or uniformly distributed in nature. So you've seen this graph before, or you've seen this such a bell curve before. This is going only from like -20 to +20, so this doesn't describe human height, but you could think of a different x-axis here that describes, for example, the height of the people in this room. There's going to be a couple people who are way down on the lower end of the spectrum, and there's going to be a couple people way up on the higher end of the spectrum, but the counts of different heights of people, for the most part, there's going to be the most counts of people's height someplace in the middle, and then they're going to have these outliers that are few and far between. So a normal distribution, when we plot it on a two-dimensional graph, looks something like this. So here we have the same sort of thing. The density is happening in the middle, and out on the edges, there's not so many instances of a thing, and it's happening also on the y-axis. So a normal distribution on a two-dimensional graph is clustered around the center. And maybe this is a little bit clearer if we compare it to a uniform distribution. All I'm doing is I'm using this scatter function, Julia's scatter function, and I'm passing it two arrays of uniformly distributed random numbers. And the uniform distribution has an equal likelihood of a number happening at any place on the graph. So here, up in the corner, it's not any more or less likely to get dots someplace in the center, someplace in a different corner. Whereas in the normal distribution, getting a corner is a lot less likely than getting a point in the center. So those are normal distributions and uniform distributions. And this might have been a thing that was going through John Snow's mind as he was looking at the maps of London. Oh, I don't have a map here anymore. There we go. So yeah, anyway, John Snow looks at the data, and maybe he formally wrote a hypothesis, like scientists do nowadays. Maybe he said he had what we call a null hypothesis. This is the base assumption, the naive assumption. And then, so for in 1850s England, the null hypothesis is that one of the null hypotheses is that bad air is causing cholera. And the way that you usually start out with your hypotheses, they get more complicated. It's an iterative process. But you start out with your null hypothesis that things are normally distributed or uniformly distributed. It depends on whether they're independent random events, or they're normally distributed if it's combinations of those events put into a more or less a natural setting. And then you write an alternative hypothesis, and you say, this thing has a different distribution, and here's why. You have some sort of theory that explains why the base assumptions are not happening. So you might call this H sub 1 or H sub A, your alternative hypothesis, or maybe you have multiple hypotheses that are your alternatives. So maybe I want to go, yeah, so we'll look at this. This is the actual map that John Snow made of Broad Street. And we put these little black tick marks for every time there was a death of cholera on Broad Street. So if we were thinking like data scientists or John Snow as a regular scientist, what we would have to assume is that there is, in these houses, every single person has a uniform random probability of contracting cholera. We're going to assume that the whole town is equally smelly, at least in this neighborhood, and then every single person should have the same chance of contracting cholera. So we assume the normal or sometimes uniform distribution across populations, but we also know that some houses could be more densely populated than others. I started to make a map to account for these things and make some infection per capita map, but I ran out of time and bailed out because I didn't know how densely populated each house would be. But if we formally write our hypothesis, like what John Snow maybe was doing if it was a scientific study he was writing a paper for, we'd say that people living in equally odorous parts of town have a uniformly distributed likelihood of contracting cholera. And so what John Snow thought is, what if we actually talk to the poor people before we just assume that it's bad air and do nothing to solve these things? So John Snow was in wealthy, educated society, and the other wealthy elite in London thought that that was a ridiculous idea, but he went and did it anyway. If you didn't know, the word statistics has the word state inside of it, and this isn't like a snapshot of reality type state. The word statistics is literally has an etymological link to collecting data about the people within a nation state. So I don't know if John Snow knew what he was doing, but what he was doing was harking back to the original meaning of the word statistics. He was doing census-type data, collecting information about the citizens in an area. I think that's fun. So we went and collected more data and learned some interesting things from the people who were actually affected by cholera. Some of the facts that he learned was that there were workers at a brewery who were completely unaffected by cholera, regardless of where they lived. But their families died, or had some of their family members died, but none of the people at the brewery died. There were children in the neighborhood who died of cholera, but they were the only people in their families who died. So it wasn't necessarily just that they were young and susceptible to cholera, because other people, old and young alike, were dying of cholera. But some children always died of cholera and were the only ones in their family to do so. And there was one woman who lived in a completely different part of London, and she was the only person in her neighborhood who died of cholera. So she's an outlier, and we can do a whole conference talk just about how to deal with outliers and whether we should ignore them, whether we should only focus on them. Outliers are a difficult thing to know what to do, but in this case, this outlier was one of the key pivotal pieces of data that gave John Snow the ability to detect the cause of cholera. So John Snow created an alternative hypothesis after collecting his data that rather than people are collecting data, are contracting cholera because of the odor in the town, people contract cholera because they're taking water from certain wells. And what happened is that people were contracting cholera from that one particular well because of the fact that there was a sewage leak getting into the water from where the well came, and people were contracting cholera from the human waste that was getting into their water. So if you look at this pump in the middle of Broad Street, this one was having a leak where the human waste, which carries cholera, was getting into the well, and people were taking water from that well. This one woman who contracted cholera from way up in a different part of London really liked the taste of the water in that well. I don't know why. Maybe it had been like that for years, or maybe it had actually had a different taste that had nothing to do with the cholera. But in any case, she sent somebody specifically down to this well to collect water for her to drink back in her other part of town. The people who worked at the brewery were drinking beer and not water. The stuff that they were drinking had been purified and been prepared industrially in a way that it no longer had cholera, or it never had cholera in it. But their families were taking water directly from the well next to their house. So anybody who lived near that pump was taking water from that pump, unless they worked at the brewery. And it turned out there was also a school nearby where children would drink water from that pump while they were in school, and when they would go home, their families were drinking from another pump. John Snow was able to put these pieces together by interviewing people, by asking questions of the data, by doing what we call maybe data exploration with an emphasis on the user, you could say, or an emphasis on the people who are affected by the model he's trying to create. I'm going to put a quote up here from the person who wrote the book, literally, about exploratory data analysis. Basically, when you're working with data and you're trying to understand the narrative, making pictures of it is one of the best ways to get insights that you didn't see were there. That's why you do it. So, what are our lessons here? 1, data is good, more data is better. 2, visualize your data. Maps can be super helpful. It could be other graphs or visualizations that you're doing. Graphics and visualizations help you both communicate what you already know and discover what you don't know. And this is a question, I think I put this on every single slide I make about machine learning. Do we actually need machine learning for this? John Snow didn't. He discovered the cure or the prevention of cholera and saved millions of people's lives, and he didn't use machine learning to do it. Machine learning can be extremely expensive to implement, and as I'll show you later, there are other alternatives that don't involve spending $1 million on a data science team that can help you get started and get on the path to getting real answers. So, yes, this is a story about, I would call it more about data exploration than about like that much hard statistics, because what we were doing here was we were just looking at data and making hypotheses, and visualizing data and making hypotheses, and doing user interviews and making hypotheses. Once we had the hypothesis, once John Snow had his hypothesis that water from this one well was causing cholera, he went and he took the handle off of the pump, and people could no longer get the water out of the well, and people stopped contracting cholera. So here we could maybe extract a little bit of a, how do we prioritize our hypotheses? What's the cost of implementing this experiment compared to the potential benefit? And removing the handle from a water pump is a relatively cheap experiment, and he actually happened to get approval from government officials, but you definitely wouldn't need to. If you felt pretty strongly that you knew how to prevent cholera, maybe you could just go remove the handle without asking. So this is a plug for doing data exploration, and that scientists and data scientists do data exploration. This is just a graph I found on Kaggle.com, which is like a statistics competition website that I thought was a beautiful overview of some data. You don't have to know what it is. It's beautiful. It's Pride Month. Live it up. This is just what data exploration in modern times looks like. I don't watch Game of Thrones, so I don't know if this actually happened or what's going on in this really epic painting. But let's suppose before we had Jon Snow looking at data for the first time, and now we have we've explored our data. We feel good about the data. We have this mature set of data. Maybe we've enriched it with other external sources. And now in this metaphor, you're Jon Snow. You're the person who's doing the data exploration, who's working with the data. I assume this dog and this guy work together. And I don't know, you have this model, which is like the sword in your hand. You're an awesome team. I like to pretend this guy also has a pet raven on his shoulder who's guiding him the whole way. Because if you just have, can I do this without making them all go away? Yes. If you just have these 3 pieces, your model, and your data, the model is could be a mental model or an actual machine learning model. If you just have those 3 things, you're still in that equation that I showed you in the beginning with the question marks. What you need is your raven on your shoulder who's helping you think about the business and tie this back to some actual users. This raven on the shoulder, I guess, is the reason that you go and you talk to the poor people. You talk to the users. You talk to whoever is going to be impacted by your data and your model. So let's assume we have the data. We know how it feels in our hands. We know different queries. We know the maximum and the minimum and the descriptive statistics. And we know what the outliers look like. And we've tied this to some real value for people in the world. We know that this will somehow connect and help people somehow. That's awesome. That's awesome. So let's talk about models real quick. A model is, you could think of it just as an equation that maps x to y. So we have some input variables. In this case, I chose ABC and not x. But we have input variables ABC, and we get some prediction, y. This is a linear and polynomial regressions. Those are models. So we have the same data in all three of these things. This model over here on the left is not very descriptive, not very helpful. It's underperforming. But this model over here on the right, we know it's overfit. It's too perfect of a model to be talking about our data. If you look at the one right in the middle, this Goldilocks just right model, we have something that is never actually perfectly accurate, but it's generally describing the data. You can't do better than that. You can't, okay, you can do this one on the right, you can do perfect, but the second you get a new piece of data, you're not going to be able to predict for that new data. This middle one, describing the data generally, is exactly the place that we want to be. So what this equation is saying, we have a function of ABC, maybe some other stuff, plus some error term, epsilon, is equal to our prediction. The error term is everything that we don't have inside of our model yet. So the first thing we want to do, or in general, what we want to be doing as we're talking about models, is moving everything from that epsilon, from this, there's other factors that we haven't considered within our model. We want to move as much as we can to consider it inside of our model. So the goal is to minimize this epsilon and put everything inside of the function. Sometimes this comes from querying, I don't know, weather.com, finding out the weather for whatever. Let's say we're doing sales predictions for a grocery store. Maybe a function of sales that happens in this grocery store is whether it's raining or not. So our model has to, in some cases, go to some external API and say, I need information from you so that I can make predictions about sales. There's other cases where maybe some input parameter, let's choose C out of a hat. Maybe C is too complicated. There's too many things. Like this is one piece of a column in our data set, and it has too much going on. So one of the things we can do is we can split C into two other columns, D and E, that are both giving a much clearer signal of what's going on. So I don't know. Let's go with weather again. Maybe this thing is talking about whether it's raining and thundering and lightning and wind, and there's a lot of wind. You could turn this into three different pieces of data about whether there's wind, whether there's rain, and whether there's thunder and lightning. These are three different things that maybe we're all living inside of one data point. And you can help your model understand the state of reality more if you break them up and feed them to the data or to the model individually. Another thing that might be happening in your model that you want to help your model with its predictive power by find one of your input parameters could be, so another example is if we have cars that are dropping geolocations every second or something like that. So we can extract from all these records that we know where it was at what time, but if we do some pre-processing, we can know how fast, what the instantaneous velocity was. And if we look at other records nearby, we can also discover the instantaneous acceleration, or was the vehicle going up a hill or down a hill? Was the vehicle in the middle of a turn or something like that? So these are things that you can take from your data, you can squeeze the data a little bit more, and you can give your model a piece of information that it might not have been able to figure out by itself, which can leverage your data and help your model along. So more data is good or better until it's not. Sometimes we have too much data, or we've included some random variable that doesn't, or some arbitrary variable that doesn't actually tell us anything about what's going on in the world. So if B and C aren't helpful input parameters, then we can do things like dimensionality reduction or PCA, and we can get the noisy data outside of the signal, like take out the noisy data and filter down to just a signal, which also helps the model perform. So regardless, so what I just talked about is called feature engineering. And regardless of what you've done with your data and what your data can tell your model, you need to understand, again, what is the use case for this? What do I want to get out of this? What sort of Y value am I actually looking for? And how will this help the people or the business or whoever I'm trying to make this model for? So what you have here is a graph of popularity of machine learning models between 1950 and 1980. This came from somebody who scraped all of Google Scholar looking for specific terms that indicated that the paper was talking about using certain machine learning models. I'm trying to give you a historical perspective of how people have been using different machine learning models, partially so that we can recognize trends and we can be not so susceptible to the fads of the sexy new models that are coming out in the world. So if you can't read I hope you can read the key, but basically we have linear regression, which is going up into the 8,000 articles world, and everything else, which is remaining almost constant between all of 1950 and 1980. So if we go back in time and we look at when was linear regression invented, we can see that in 1805, some person was figuring out how to predict where comets would be. And he used linear regression. It happened to also be invented by this guy named Gauss, who thought it was so easy or so obvious to use linear regression that he didn't even publish a paper about it. It was almost one of those, an exercise left to the reader, because for Gauss it seemed so painfully obvious. I don't know where Gauss went, but, Okay, so anyway, linear regression was invented in 1805. Yes. Then the double helix was invented in 1953, but before that, Alan Turing had already theorized about the ability to write genetic programs which would evolve, share genes with each other, and learn to solve problems through the process of evolution. Then it would be in 1981 when somebody named Forsyth actually wrote code that evolved to solve problems. The neuron doctrine, this concept of the cells in our brains, came out in 1894, way off the end of this chart. And there was the concept of artificial neural networks had a theoretical foundation that was laid in 1943, but it wouldn't be until 1958 that Rosenblatt invented the actual first artificial neural network. So this is to put in perspective the historical context and the scientific and real or life science foundations or inspirations that go into the different models or some of the models that are happening on this graph. But then, after the 1980s, we see that the graph becomes a little bit more interesting. Linear regression falls out of style. Logistic regression makes an upswing, but then ultimately also falls out of style. And neural networks and deep learning are starting to take precedence. Something that happened in this time also is that people realized that they didn't want to, or maybe it was impossible to get to the point of actually making generalized artificial intelligence. And they started using these different machine learning techniques to make specific predictions in specific instances, rather than having just a machine that could think like a human, having a machine that could think about good enough or sometimes better than a human within certain contexts for a certain business goal. I have friends who have talked about when they were, I don't know exactly where they were in school, but it was before the neural network actually took precedence, and they had professors in school who told them, you'd never use a neural network. It's impossible to be able to get the the resources you need to get anything useful out of this. Same thing with genetic programming. These things have had, even within these large trends, they've had smaller fads where they come into style. And it's still, I think, despite the popularity of what's being used, I think we'll see that there's also no definite best algorithm for one specific case. So I would invite you to remember that all models are lies. They're all wrong. But the real question is, how wrong do they have to be for them to not be useful? This is a quote from George Box. He's cited many times as one of the best statistical minds of the 20th century. So your decision is to choose the best lie. So I'd say whether you're trying to do optimization or gradient descent, you're doing some Lagrangian calculus to optimize over some cost function, whether you're using genetic programming to evolve programs that understand the mechanisms that create things that are lifelike, and or just using Bayesian statistics to infer the likelihoods of things. Thinking like a data scientist means making pragmatic choices. This is pragmatic choices about models, what you think is what is the right model? What is the right purpose for this model? Yeah, so this is why when we look at this graph of linear regression being the most popular thing for 200 years, it's really easy to implement a linear regression model. And maybe that's the pragmatic choice for your organization, or at least the good null hypothesis is we'll implement a linear regression or a basic polynomial regression. We'll set that as our null hypothesis, and we'll make alternative hypotheses about better models on top of that as we iterate. Talking about pragmatic choices, I feel I also have to bring in the concept or bring in the topic about ethics when we're talking about data science. And I don't think I've mentioned any of these things. I think talks that mention any of these things are good talks, are good things to mention, but maybe we should have been having conversations about what we're building and whether it's the right thing to be doing. Maybe we should have had that talk 20 years ago or something. I think we're past that time. And what I would say, again, is looking at the world, looking at concentration camps in the United States and people being processed for or criminalized for saving refugees in the world, we are in positions of power as data scientists. We're building things that can be weaponized, and we're building things that will be weaponized. And so, again, I think thinking like a data scientist is making pragmatic choices. And one of those pragmatic choices is not to build shitty software. It's not to build things that could be weaponized, and it's to organize ourselves and get away from maybe the direction that we're going in under the surveillance capitalism world we've built for ourselves. So I'll leave you with that. Thank you very much. My name is Emma Grasmeder.